Thanks. I'm sorry I'll be stuck here close to my laptop because the remote doesn't want to work. Don't know why. I'd like to start by thanking Benjamin, Dan, and Murray for organizing this wonderful workshop. It's been really great. I'm glad I got the opportunity to speak here. So my talk will be focused on one single topic, and that has to do with the prediction that if you're working with a system of photons or polaritons and you've managed to make them interact, say repel each other, then the prediction is that given certain conditions, you don't actually, it's not worth trying to switch the sign of the interaction and to make them attract. You will actually see exactly the same non-equilibrium dynamics. And so my talk will focus on that, not be a big firework display of different topics. This is something that I've worked on together with my now postdoc, Andy Lee. And I thought that if it's close to lunch, if you're ready to go into your pre-lunch nap, I'd start with an executive summary, which was nicely presented by Benjamin yesterday. So here it is. The important message is really that cavity QED physics is intrinsically non-equilibrium, and your intuition, which works very nicely, I bet, for equilibrium physics, can lead you down the wrong path. And I wish that Benjamin had warned me about this half a year ago. But so it goes. So I'll say just a few words to motivate this talk further, and then I'll start with one of the simplest systems that you could think of in this context, a Bose-Hubbard dimer, not so different from the Jaynes-Cummings dimer that Andrew Hauck was talking about yesterday. And I'll talk a little bit about what happens in the closed system and then what happens in the driven and damped system. And then I'll take that insight one step further and make it a little bit more abstract, and hopefully that way get to a place where it might also apply to whatever system you're considering, as long as it can be described in the formalism of Lindblad-Master equation. So I'm considering Markovian open quantum systems here. And the form, I'm sure, is very familiar to you. So we describe this in terms of a density matrix, and that the evolution of that density matrix is governed by multiple terms. The unitary von Neumann part with the system Hamiltonian, and then a number of terms that describe dissipation and dephasing. And as you know, all the observables that you're interested in, you can then calculate perhaps, so this S, I suppose, was meant to that maybe there's a steady state, and you can calculate observables in that steady state. And what's really neat about this is that you can really think about this and explore what can you learn about dissipative phase transitions. And I'll show this slide once more. You saw a version of it yesterday already. This is again based on a paper from the Lukin group, and compares what is a quantum phase transition. All of you know that. You have to know the Hamiltonian. You're interested in the ground state, and a phase transition happens when the ground state switches. You have a crossing from one type of state to another, and that's what you're interested in. And on the side of dissipative phase transitions, the object of interest now is this super operator L that you saw. If you allow me to go back one, I can't do that with the remote. So here it is. That's the abelian super operator on the right side of your master equation. It's as an operator, it's not Hermitian. You're interested in the steady state, which is the guy that comes with a zero eigenvalue. And if you look in the complex plane of eigenvalues lambda of the superoperator, you get a whole bunch of eigenvalues. And if there's one that approaches the steady state, and oh, thank you. That approaches zero here, then you've reached a point where a dissipative phase transition occurs. And so let's see for this really, really simple system of Bose-Hubbard dimer, first what is the ground state physics. So you have two sites. They might be cavities, they might be resonators on a chip, whatever you choose. And then they come with a certain frequency, which is your on-site energy, and the photons that are, or the bosons to start with, they might repel or attract, which is symbolized here with a plus or minus, and that's your on-site repulsion or attraction. And then the bosons can also hop from one side to another with a hopping strength that is called J here. And so if you're interested in, well, what's the ground state physics, then let's quickly look at it. If U is positive, then you have repulsion, and once you feed all your bosons into the system and let them find the ground state, then if it's an even number, then it's particularly simple. They will just split up into n over 2 and n over 2 on the left and right hand side. And if you face the attractive case, then it's slightly different, right? Because now the bosons actually like to be together, and so they will go all into one side. But of course, if you have a little bit of hopping, then you get a coherent superposition of all of them on the left and all of them on the right. And now we listen to Benjamin and be prepared that in this non-equilibrium setting, things might be different. So in this case, the bosons are actually created by a coherent drive. In this case, I chose to write it such that it's only acting on the left. You could do something where it's left end on the left and right, and there's now also dissipation, right? These bosons can actually escape or be absorbed, and that we'll have to describe in terms of a master equation. The rotating frame Hamiltonian, once you take into account that you're driving your system at a certain drive frequency omega d, you go into a rotating frame that eliminates the time dependence of your drive term, and then you can look at steady states of the density for the density matrix, so the time independent solutions of this equation. And that system was studied by Mohammed Hafezi and colleagues, and what they found was that in the case where there's repulsion, so we have a positive U, there's a region in this diagram which shows the strength of U on the x-axis and the strength of the hopping J on the y-axis. That's a region where the symmetry between the two sides is spontaneously broken, and you have steady states where there's a sort of self-trapping, and bosons like to bunch up more on one side than the other. And my postdoc and I were amazed by that, and we realized that in this paper, Mohammed did not talk about attraction, and so Andy started doing a simulation, and on one day he came to me and said that, you know, whenever I try for negative U, I actually see the same thing as for positive U. And I didn't believe him. but I should have. So I said, okay, if you want to convince me, then I don't just want to see numerical solutions that convince me that we can look at this analytically, and you can. And so one way to do that is to pick an observable. Let's say we want to understand what the expectation value of A1 does as a function of time. And so from the master equation, you derive your equations of motion, and you can do that once for the positive U case, and then for the negative U case as well. And so let's try and see whether we can manipulate the upper equation such that it looks like the lower equation. So manipulate it in such a way that this positive U actually turns into a negative U. And one thing that you could try is, let's take the complex conjugate of that upper equation. Then the result is this, right? You turned your I into negative I. This sign changed as well. And to make the two look more alike, I'll multiply this equation by -1. At which point it looks like this. So these two now are parallel. The dissipation comes with the correct sign. There appears to be a sign switch of your delta omega. This one here we've switched, right? I can even, if I want to follow my notation and always keep the sign of the interaction term actually as a subscript, then I should write this in this form, right? It's now plus 2u sub a negative sign, and on the hopping you've changed your sign as well as for the drive strength. And so if you want to kind of present that result, then you would say, all right, so we define something where we collect all of our Hamiltonian parameters in some symbol p, and if we do that, then it looks like the expectation value of A1 for this set of parameters, if I take the complex conjugate of that, I get the same as if I had calculated A1 in the attractive system case, but with the opposite sign of all my Hamiltonian parameters, right? The delta omega has to switch sign, so does J and epsilon. And of course, your calculation is not quite done yet, because you have a whole hierarchy of equations. You would now have to find and prove that this one here follows the same kind of pattern, and that's something that a theorist can do, and it's mildly amusing. There's a big equation that says that for all your operators that you can write in this product form, this symmetry actually holds. So you can calculate all these expectation values for the repulsive system, take the complex conjugate, and you get what you would have found in the attractive case with the inverse sign Hamiltonian parameters. And so if you allow me to just summarize that briefly, then I would say you start out with a Bose-Hubbard dimer that is repulsive, and here are your other Hamiltonian parameters. You have a damping rate gamma, and you can calculate whatever expectation values you want. And this now has been mapped to the case where your system is attractive, and the other Hamiltonian parameters have changed sign. The damping rate is still as it used to be, and if you want to get expectation values for this system, then you can calculate them from here and take the complex conjugate. If it bothers you that the hopping has changed sign and the drive strength has, then there's actually a simple gauge transformation where you take A1 to negative A1, and at that point the only thing that has to be adjusted is delta omega. So if in the repulsive system you're driving the system red detuned, then over here it would be blue detuned, and vice versa. So and interestingly, this now really means that we can take this phase diagram that Mohammed obtained for positive U, and we can turn it into a phase diagram that now extends to negative U, to the attractive case. So there must be this symmetry. And so at this point, there are these two characters. They usually sit up there in the balcony, and they have criticism, and so they don't believe this yet. So the first thing that they could say is, well, this doesn't seem right, because if you take the drive strength to 0, right, you should get equilibrium, and how could in the equilibrium case, how could attraction and repulsion be the same? And at this point we let Benjamin remind us that well, for this intrinsically non-equilibrium system that we have in cavity QED, this limit is actually the most boring limit that you can consider, right? It's all the bosons go away, right? If you don't feed them in with your drive, then you're in the vacuum state, and you know the vacuum state indeed is the same no matter whether you have attraction or repulsion. So that's all right. And then our two characters from up there, they say, well, okay, fine. We'll feed in some bosons by using finite temperature, right? We just heat this up. Repulsion and attraction must lead to different results, clearly. And that one is a little bit more subtle. So you could say, all right, so here's the master equation that I should look at. I'm now explicitly including terms that have finite temperature, and actually, ouch, there should be a dagger here. Just imagine. But even if the dagger was there, this equation is wrong. And we don't often think about that much. So one thing that should bother us immediately is that it's not actually clear what energy is going into this Boltzmann factor here. So that seems fishy. And indeed, if you open your favorite open quantum system book, then you'll find that actually the jump operators that have to go in here, they should be of this form. They should be Hubbard operators going transferring you from one eigenstate of the system Hamiltonian to another one. And then, in fact, the energies that should go into the Boltzmann factors are just the transition energies, right? And so if I do that, then applying this map actually does not transfer from the attractive to the repulsive case. So in fact, if you applied the mapping, you would get a result that is just a corresponding partner system that is not very physical. Now, this insight that there's somehow this mapping, and you can go from repulsion to attraction, that was not entirely new. So if you go through the literature, you can find examples of that. So Mark Dickman, who we talked to, said, I noticed that for when I studied a driven damped nonlinear oscillator, and in this paper up there, I mentioned that there's this funny symmetry. And likewise, talking to Jonathan Keeling, he and his group had discovered that and noticed that multiple times, once for non-equilibrium Dicke model, and once actually for a transverse field XY model. And so the question is, can we formulate this mapping in a way that is a little bit more system independent, and hopefully also get around this awkward thing of calculating the whole hierarchy of expectation values that the system might exhibit. And so we said, all right, we'll try. And one thing that might help is to it got rid of all my animations. What a pity. So consider some system Q1, and it's described by this master equation. And since we saw that there's something going on with complex conjugation, it's not so far-fetched to try and investigate what happens if we apply the time reversal operator T, which all of you know, I suppose. It's an anti-unitary operator. You can, if you do it right, you can represent it as a unitary transformation and complex conjugation. And so let's see what this object does. We take our density matrix rho and we sandwich it as usual with T and T dagger. And note that the map going from T, looking at the evolution of this new object rho T, that is not backwards evolution or backwards in time evolution of the density matrix. So let's check what kind of. Give me 1 second here. I'm really unhappy about this animation having gone away. That is really strange. Oh, there it is. I just had a double slide. There we go. All right. So you sandwich your density matrix, and let's just explore what time evolution we find for this new object. And so you start from up there, you sandwich your density matrix with T and T dagger, and on the right-hand side, initially the T and T daggers are outside, and then you manipulate that a little bit, and you drag the T's and T daggers inside. So over here, it starts looking more like an actual right-hand side of a master equation. Right now, there's still a plus I instead of a negative I, but you can manipulate that further and get it into this form where I've compensated for the missing I by going from H to negative H. And you see that potentially your jump operators have changed. They're now sandwiched by T and T dagger. Fortunately, in many cases, these jump operators are actually time reversal invariant. And so if you have a photon annihilation operator, for instance, it will not be affected by that at all. And note that I'm assuming that the Hamiltonian is not breaking time reversal time reversal symmetry. So that's why I got from T, H, T dagger back to H. Good. And so this equation clearly is of the right form for a Lindblad master equation. The one thing that we have to do is check whether it's physical, right? So I already mentioned for the jump operators that that's usually not a problem. But the going from H to negative H seems interesting. So under what conditions can that be physical? Well, one is if your Hilbert space is finite dimensional, then going from H to negative H just inverts the spectrum, and you don't have any problem with unboundedness. The other scenario in which this is a fine idea is if this H is actually a rotating frame Hamiltonian, then being unbounded below at large negative energies is not a problem either. And so finally, with this equation in place, we can also verify that if I want to calculate an observable in this second system, I can obtain that by calculating this for system 1 and in the right way apply the time reversal operation and complex conjugation. And so this is summarizing this. So I hope that I made this clear enough that you can actually take this and check whether it leads to something interesting in your system of choice, and to maybe convince you that indeed this is not just limited to this Bose-Hubbard dimer. Here's an example where perhaps you're considering a spin lattice. So in this case, I'm looking at an Ising spin lattice, 1 spin per site, has a certain energy omega here on for flipping the spin, and then there's a sigma z interaction, which can either be antiferromagnetic or ferromagnetic. And I've already chosen a lattice that makes life a little bit more interesting, because for the antiferromagnetic case, you know that the triangular lattice has geometric frustration. And so if you're studying this in the context of a system where the spins are driven and can also relax, then this is the right place to be to explore what this mapping actually does. And indeed, it takes you from the ferromagnetic to the antiferromagnetic case, meaning that what originally seems very interesting, namely having a frustrated antiferromagnetic system, that gives rise to exactly the same results as the system that has ferromagnetic coupling and has no geometric frustration. So in a way, this non-equilibrium setting makes life a lot simpler, which can be good or bad. So clearly, if I can reproduce this the exact dynamics with the ferromagnetic case, then I shouldn't argue here that there's very interesting physics going on because the system is frustrated. And so to summarize this, I hope I convinced you that for the Bose-Hubbard dimer, you can extend this to a lattice easily. The equilibrium physics indeed is very, very different, and probably your intuition works great there. But under the conditions that I mentioned, you will see the exact same non-equilibrium physics. And so in a somewhat more abstract and general way to formulate this, I showed you that you can employ the time reversal operator and actually map the system with Hamiltonian H to one with a system Hamiltonian negative H, and then the two, once you've checked that the number 2 is indeed a physical system, the two will show the same dynamics and hopefully help you understand better what your system, whether in your system it's important that there's frustration, perhaps not, whether it's important that the nature of the interaction is repulsive, perhaps not either. And so just to close, the one thing that my postdoc and I are working on still is to hopefully get back to a more intuitive understanding of non-equilibrium steady states and dynamics. I remain kind of amazed and puzzled that things like frustration and the nature of the interaction may be irrelevant to the dynamics of a system when it's in non-equilibrium. And so maybe you have ideas. I would love to hear them. And then finally, I'd like to thank Mark and Jonathan for guiding us and telling us about results from their groups, and also David Schuster and Andrew Hauk, who are my collaborators, and I'm very thankful for that. And thank you for your attention.
Very nice talk. So despite my quote, I think I want to ask a question that maybe will lead to a contradiction of my statements. In the two parts of your talk, I wonder if the equilibrium version of the model can give us some intuition. So I might be wrong about this, but I think I've heard that the Bose-Hubbard model, if you also flip the sign you have particle-hole symmetry, then nothing changes. So is the non-equilibrium version of what you have shown a consequence of a particle-hole symmetry in your model? And so that's part one.
I will
And I think there's
say
some
I
experiments
have
by
to
the
think
Mega
about
Blocks group that
that.
actually did this, where they switched the sign and showed that everything was the same if you're at half filming, or at the lobe.
I would like to think. I would like to think about that. I guess I don't know. So when you take this mapping to this more abstract level, there's not really I don't see how to incorporate the concept of particle hole symmetry into
the universality class of the transition that tells you this, and the fact that you're not in equilibrium doesn't necessarily change that in this case. So then the other part of it is that looking at the spin version. So in the equilibrium version of that, when you have geometrical frustration and the triangle lattice, that doesn't give you qualitatively very different dynamics than the non-frustrated version, in the sense that you don't have a spin glass in that situation because there's no disorder in the system. So if everything's ferromagnetic and there's spins everywhere, there's no disorder. And so I guess again, it's not quite surprising to me that if you flip the sign, you don't get something in the excited states that are very different, because the degeneracy of the ground state, which is what the frustration gives you per plaquette, is really a statement about the ground state, and not about the dynamics, which is what you should compare between the two. And that degeneracy wouldn't carry over the same way in the excited states.
Yeah, I agree.
So I'm contradicting myself.
So I guess my question as an experimentalist would be, so can I break this with some form of math engineering, like putting in some tailored noise if I want my antiferromagnet to be interesting again?
So I think I'm not sure about whether the feeding in noise or bath engineering will help, but I think so one thing that Andy and I are working on is to get a better sense of what systems for what systems is this still physical, because as soon as you put terms into your Hamiltonian that, once you take the negative version of it, make no sense, then I think you found a system where really the nature of your interaction, for instance, remains important. But for something as simple as the Jaynes-Cummings dimer that you've been, or Andrew has been working on, and I think there I don't see something simple that you could do that would make the two cases very different.
I have a comment about the dimer and the Bose-Hubbard model.
Yeah.
In the non-equilibrium case, actually, you can find out that, or you can show that the attractive view is symmetric with the repulsive view. So there will be a continuum that is symmetric around zero, and for the attractive view, you form bound state from below. In the repulsive view, you form a bound state from above. That is exactly symmetric, but from above. So I'm not sure, but I think it's possible, if you think in this way, since the states are symmetric, that the dynamics would be somewhat indifferent or invariant under that transformation, because the dynamics will mix all those states and they're the same, except that sometimes they're from below, sometimes from above.
Okay. So in your case, when you say continuum, you're actually discussing this at the level of both the bath and the system are treated coherently.
Some scattering states, right? If you have a dimer in the Bose-Hubbard model, there will be some scattering states and potentially a bound state depending on the strength of the attraction or repulsion. So the scattering states, they are very close in energy. That's why they form a continuum. And the repulsive, if you have a bound state, it will be split from that, but there's actually a possibility for repulsively bound states and attractively bound states, depending on the sign of view. And these are symmetric in the Bose-Hubbard model.
Mm-hmm.
there's a lot of work on this.
Is part of this related to the difference between heating and cooling? And that when you're deuterium on one side or the other side, you're into a hot state versus a cold state, and so that's why you're inverting the spectrum?
That I'm not so sure about. So what I showed was were results where we actually just set temperature to 0, so that there was no thermal heating.
You're into like either negative 0 or positive 0.
Right, and I think so. I try to motivate that if you actually increase temperature significantly, you'll be forced to use the correct jump operators, which actually, even for the Bose-Hubbard dimer, it's not A and A dagger. You will have to use the correct Hubbard operators, and in that case, if you apply the mapping, you do not simply go from repulsive to attractive. So this map doesn't. You get an unphysical result.
I think my question is a follow-up to that question. So could you just explain a little bit more on how you would convince the critics on the balcony about the finite temperature case and how their argument doesn't work?
Right. Wait, where is it? Right. So if you look at these terms here, right, then in fact, as you sum over J and K, which enumerate the eigenstates of your system Hamiltonian, then the rates for positive and negative transition energies will be very different, right? And as you employ your map, the only thing that happens is that these Hubbard operators in the dissipative part will be sandwiched by T and T dagger, which will not do anything. So the map will lead you to a system where suddenly the rates for transitions going upwards are the large ones rather than the ones that are exponentially suppressed. So that would be unphysical. So in that case, applying this mapping leads you to something that it does not describe nature, and that is something that you have to check. Applying this mapping is at that level it's just a math game, right? And then you have to check that the resulting master equation, both in terms of the Hamiltonian as well as the dissipative part, whether it's physical.
I mean, it's flipping the temperature of bath to negative.
You can phrase it that way, sure.
Okay, if there are no further questions, let's thank Jens again and all the speakers.